Hello class. Today we're going to be looking at logistic growth model. This is a really interesting exponential equation, and it has a lot of applications in our life, when you're studying biology and such like that. So let's go ahead and take a look. One of the things that you can use to the logistic growth model is on watching capacities of wildlife in a contained environment. There's an island in Lake Superior called Isle Royale, and there are two populations of creatures that live on there whose survival is needed for each other. You wouldn't think that one needs the other. The two animals are moose and wolves. Now the wolves will eat the moose because it helps bring down that population of the moose herds so that they don't run out of food, because it is an island. They cannot just travel to get to more areas of food. So it's a delicate balance of those two. Now, if we were to leave or reduce the number of wolves there or eliminate the number of wolves, the moose herd would grow to a certain amount of number of population, and then they would start dying from starvation because that island has something called a carrying capacity. And that's a real problem right now in Isle Royale. They got down to 2 wolves, and then the humans intervened and started bringing some other wolves down there. So let's assume that the wolves were not brought, and we were going to do a growth of the moose. It would be an exponential growth, so it would be coming up like this, but there would be a horizontal asymptote that would be the carrying capacity, and this growth would come about to here, and it would just flatten out there, because after that there is no more food shortage. There would be a food shortage with that many moose, and so the fluctuation will go up and down and up and down, but never ever cross this line. So let's take a look at the model itself. So the logistic growth model can be represented by the function in terms of time, so f of t, or in the previous one we called it a. And that's going to be, it's a fraction. C is the numerator, and on the bottom we're going to have 1 plus a small a times e that's raised to the negative b t. And let's determine what all these are. We knew from the last one that a is our final amount. Our small a, this time we're going to use small a instead of a sub 0. That's still our initial amount then. The b is the rate of change. And it's going to be positive because it's a growth model, and then it's, so there will always be a negative in there because the negative is part of the formula. And then t is going to be our time. Those are all pretty much the same thing. C is going to be a horizontal asymptote at y equals c, because that is the population or the carrying capacity that cannot be exceeded. So C is the carrying capacity. Or sometimes it's called the limiting size. So let's apply this to a learning theory project where psychologists discovered this particular function, f of t is equal to 0.8 over 1 plus e raised to the negative 0.2 t. And that's modeling the proportion of correct answers after t learning trials. And they discovered that there was a limiting size or carrying capacity there. So let's find the proportion of the correct answers prior to learning the trials, before they took place. So before they took place, prior to, that means the t is going to be 0. No time has passed. So we're looking for the function of 0, and we're going to put 0 in for the time. So that's going to be 0.8 over 1 plus e raised to the negative 0.2 times 0. So let's do these in small pieces so you can see it. Negative 0.2 times 0 is just 0. Well, e to the 0 is 2, so we have 0.8 over 1 plus 1, or 0.8 over 2. So that's going to give us 0.4, and that's the number of correct responses. Or we could say that it's 40%. So then the psychologists gave their subjects time to have trials to try to learn the pattern of what they're doing. And so after 10 trials, so they're going to have t is equal 10. Let's find out the proportion of correct responses that was supposed to underline. So we're going to do f of 10 is equal to 0.8 over 1 plus e to the negative 0.2 times 10. Just go ahead and put this in your calculator. Later, there we go. And you're going to get 0.7, or 70% correct responses. So then we get to this answer, what is the limiting size of f of t, which is the proportion of correct responses. As you continue to take learning trials are taking place, what's the highest we're going to get? And this one requires no math. Remember, c is the limiting size. If you remember where c is, it's right there. It's the numerator. So 0.8, or 80% correct responses. So this is the easy question of logistic growth problems.